Okay, cool. Thanks, Toth.
Mm.
Okay, so we have a couple examples here. Root is looking like it's this big array, but really the root is going to be a node. And we're going to talk a little bit about what that means in a second here. And then the output is going to be 3. So just looking at it like this, we don't know much about the context of what the input is going to be. Is this an in order? Is this a pre-order? Is this a post-order representation of a tree? I don't really know yet. And I'm going to grab the picture in a second here. But in this case, we have another root. Output is 2. And then we have some constraints. And so the constraints are that the number of nodes in the tree are going to be between 0 and 104. And the value of a particular node can be from -100 up to 100. And this is the image that we're going to use. And I think I can just paste this in. There we go. And so looking at this initial example, we can now start to map our understanding of what this tree structure is going to look like. We see that 3 is represented here as the root node. And then we have 9 as the left child of 3, 20 as the right child of node 3. And then 9 has no children. So inside of this input, that's represented as 2 null values. And then we have 2 children for 20, which is going to be 15, and then 7. So first thing I would do here is I would just start off and I would have, I would write out my IOCE. So input, output, constraints, and edge cases. So my input is going to be a root node of a binary tree. My output is going to be an integer. The constraints that I have are the number of nodes in the tree. So number of nodes is going to be between 0 and 104. And my edge cases, we have, in this case, actually, sorry, constraints. So this is where I would maybe start asking some questions if this was like in an interview context. But seeing that the constraints are saying the number of nodes, this isn't really how I would consider constraints in most interview cases. Usually I would consider this as an edge case. Or in this context specifically, I would say the edge case would be an empty value, so an empty node. So if we get a node, for example, where the root equals just this, how would we account for that? And my gut tells me that there's going to be some simple return value if there isn't a value attached to it, probably 0 or undefined or null, something like that. And in a little while, we'll be able to run this on LeetCode and check the tests. But constraints usually are going to be more along the lines of space and time considerations. And sorry, Elliot is trying to interrupt here. Okay, so and what I mean by that is like y'all got into some time complexity. We had the time complexity and space complexity lecture. So we would be saying something along the lines of this needs to be done in linear time, or this needs to be done in quadratic time. This needs to be done with O of 1 space, which would mean that we can't add any additional storage within that. Now, there weren't any specific constraints here, so we'll just label them as none. But something that you could do in an interview context would be to solve this problem in kind of the naive way, which would mean your first instinct, however you can solve it, and then come back. And if you have ideas on how you could improve it, even if you don't implement the improvements, telling your interviewer, hey, I think this solution here will work, but I see this and this as an issue potentially in terms of space or memory usage. And these are the things that I would do to improve it. I would, instead of using a nested for loop, I might break these out into 2 separate loops to increase the time or decrease the time complexity. And it's going to be a very use case specific thing, but interviewers would love to hear just your general thought processes on how you would improve the efficiency of your algorithm. So we have our input, we have our output, we have our constraints, which are none. We have our edge cases, which I'm starting off with just an empty node. I can't think of any other initial edge cases, but if we do run into any, we will work through that. So let's start out with a couple ideas here. So initially what I'm thinking is that we know that we're given this root. And I know that every root, every tree is going to have a value. I know every tree is going to have a left, and I know every tree is going to have a right. Now the value of the tree of the left and right can be another tree, or it can be null. And this is just a general understanding of how trees work, that every tree that is constructed is going to have some value in each of these here. It's either going to be a value or it's going to be null here. So I would imagine in this case, there would be a constructor, and inside of that constructor, for the tree, these three values would be instantiated. And we can confirm that real quick over here with this here. So on LeetCode, they will generally give you the constructor function for how the data structure is supposed to be implemented. It's super important to look at. And in this case, it's looking like, okay, they're saying val is equal to undefined. Then if that's true, then the value is going to be 0. Otherwise, the value is going to be val. Same thing for the left, it's going to be null or left. Same thing for right, it's going to be null or right. And so they're actually expecting that you might be able to pass in a left and a right here when you're constructing the tree node, which is really useful when we start to navigate through this. In terms of max depth, we are likely not going to have to worry about constructing any nodes. In this case, we're just looking through an existing tree structure already. But there are going to be several problems that are going to utilize this exact same kind of idea. And you'll see this as a pattern moving forward. So starting out, I know I'm going to be starting at 3 because I'm given the root of a binary tree. I also know that a binary tree has a left and a right child. And in this case, the way that it's written out, I can also tell that this isn't a binary search tree. So this is not a very specialized tree. Binary search tree means that the left value of the tree is always going to be less than its parent, and the right value is going to be greater than. In this case, we can see that 15 is less than 20, but we are then passing in 7 here. And usually I think in a binary search tree, I would see 7 become or 15 would become a child of 9 first, and then we would move forward from there because insertion order would matter at that point. But in this case, it's a binary tree. So all that means by default is that I have a left and a right value. Also, I guess I missed the easy observation here that 9 is greater than 3, and it's on the left of 3. So this also is indicating this is not a binary search tree. So starting out at pointing at 3, I want to be able to traverse through each node and track the depth as we're moving through each of these nodes. So that makes me think that some sort of recursive call is going to be a potential solution here. So if I can recursively call the next node that I want to look at and somehow keep track of the depth as I'm going through, then I think I can just update a max depth value as we're going along, and only update it if we have a new max depth that can update that value. So I'm just going to start writing some of my ideas out here. So I know I'm starting at root. So starting at the root, I would like to store max depth and update it whenever appropriate, meaning current depth is greater than max depth. And since we're only trying to return the max depth, I don't need to worry about where I found that depth. I don't need to worry about how many times I found that depth. So I only want to update it when current depth is actually greater than max depth. I don't want to waste any extra time. So from here, like I said, I'm thinking about doing a recursive call. So I want to recursively call the next node and pass in current depth. When I'm within that recursive call, I'm thinking that I want to check to see if there are any left and right children. I'm trying to think if there are any base cases or what my base case would be in this recursive call. What would I need to know in order to be able to break out of this? So if I go to node 9, for example, and I tried to recurse on its left child and the right child, I know I'm going to run into some problems because the left and right child are null. So I need to decide if I want to even go to that link. So I could check to see if 9 has a child on the left side or the right side, and then recurse if so. So I think I'm going to do that. I'm going to say if there are no children, we're just going to return. Otherwise, we're saying there are children, and we could get more granular with this, but I'm just going with my kind of initial instinct. And I'm going to say there are some children. We don't know if there's a left or a right in this case, but I can say if there is a left child, then recurse on left child and increment the current depth. And the same thing, I would need to recurse a second time. If there is a right child, recurse on the right child and increment the current depth. So I don't know if this is right or not, but this is sort of feeling like it's in the general direction. I know I'm gonna have to call this recursion function, so I would say something like invoke recursive func with root and probably 1 as the initial depth. And also we need to check here if the current depth is greater than our max depth. Update max depth. And I know at the very end also I need to return my max depth. So this feels like a good start. It might be the solution, it might not, but this is now when I would step back and make sure that my solution maps with this kind of general initial idea here, this initial visual. So we're going to start at root. We're going to store max depth. So we're going to say max depth here. We don't know what it is yet. We don't need to worry about storing anything else at this point. And it looks like we're ready to start trying to step through this function. So I'm going to start out, and max depth is going to be equal to 1. And the reason for that is we're going to invoke the recursive function with root and 1. So this is going to equal 1, and the root is 3. So then from there, I'm going to recursively call the left child, and I'm going to increment the current depth. So I'm going to go to the left child. In this case, we said there is a children. We check to see if there's a 9 or left and a right. There's a left and a right. So I can go down to 9. I'm going to increment the current depth. So now current depth here is going to be 2. And we are now at the beginning of this recursive call again. So now I'm going to check to see if there are any children at this point. And there are no children here. There's no left and there's no right. So we're going to return. And anytime that we return from a recursive call, we're going to return up 1 level from the past call that we made. So in this case, we're going to return back to 3. Max depth when we got down to 9 was 2. So we know that's going to be that. In this case also, I should clarify here, there are, this is a kind of helper function way of writing a recursive call. There's also pure recursion, where this could be the entire function that I'm calling over and over again. In this case, I wrote max depth equals 2 down here, but actually max depth is going to be updated in the global context, or not global context, but in the execution context, just outside of the recursive call. And we're going to see this in code in a second here too. So we don't really need to worry about this right here. We can always just update max depth whenever it needs to be updated. So now we're going to go down to the right child. We returned after going for this initial left child call. We went through 9. We tried to recurse further. There were no children. We returned. We got back to 3. So now we're finally onto this next line where we're going to check to see if there's any right children. And there is. 20 is a right child. So we're going to point at 20 and we're going to see, does 20 have any children? Yes, it does have some children. Okay. Does the current depth, is it greater than, current depth is 2. Is it greater than our max depth? And the answer is no. So we're not going to update. But there is a left child. So we're going to go ahead and go to our left child. And we're going to update our current depth. And we are going to check to see, again, are there any children here? And now I'm starting to see an error because there are no children. Current depth is set to update after this return call. So with the way that I wrote this algorithm, I would return now back to 20, and I would have never gotten an opportunity to update current depth. I believe I ran into that error here. I just didn't catch it on 9, but I caught it on the second time through. So now I know that the order of operations here needs to change. I know this return call needs to happen after I've checked to see if current depth needs to get updated. There's probably different ways that we can write this again, right? But this is my initial kind of idea, my naive solution. So I'm going to stick with this for now until I'm sure that it's going to break. And then later on, we can talk about maybe trying to make it more efficient if there are ways that we can identify that. So now we're going to say, okay, we got down from 20, we got to 15, current depth is updated to 3, current depth is greater than max depth, so we're going to update max depth. And then we're going to check to see if 15 has any children. There are no children, so we're going to return. And again, we return 1 layer up. We just go right back to 20. Current depth at 20, if you recall, was 2. So now we're going to go down to the right child. We just finished this call on the node 20. So now we're going to go into the right child, and we're going to do the same thing. We're going to check here, current depth, and we can already see what the answer is going to be, but the computer won't know until it reaches the very end. So here we can say current depth is 3. It's not greater than max depth, so we're going to stop there. And there are no children, so we're going to return. We return up to 20. We have done both our left and our right call, so that function is done with. And now we're going to be returning back to the original function invocation. And we are done with our recursive call. And now we're going to return max depth, which is 3. Okay. So I feel okay about the solution. I did catch one error with the initial implementation. So from here, I think I would generally try and either test it or find another set of inputs to just sanity check my solution. Given the time that we're at right now, we're going to pretend that we went through and checked another set of inputs. And we're going to go ahead and walk through the code solution for this. So I'm going to take all of this and we're going to go over to the code. And we're going to, that's not what we want. And we're just going to kind of check through here. And I'm going to actually comment this out for now. So we know that we want to start at, the function is going to be bar max depth, because that's given to us. It takes in a root. And we're just going to start through and line by line with our pseudocode, write in what we think we need to have in here. So we said on line 34, we're going to store max depth. So we're going to say let max depth equals 0 to start with. And we know we're going to have a recursive function. So we're going to build a recursive function. And we know that the recursive function is going to call the next node and pass in the current depth. So for trees, I like to be explicit and say I'm passing in a tree, and the depth is going to be whatever we're passing into it. So I'm not going to build out the recursive call yet. I'm going to make sure that I'm getting through my skeleton first. So I want to be able to call my recursive function, and I want to pass in initially the root, and we said that we're going to start with 1. So we're going to pass in 1 here, and we know we're going to return our max depth as well. Okay, so now we're going to try and build out this recursive function. So we want to say if the current depth is greater than max depth, update the max depth. So there are ways to do this. Easiest way is with math.max. So we're going to say max depth is going to be equal to something, and math.max takes in 2 arguments. It takes in that they're going to compare against. So we can pass in the current max depth, which right now is 0 on the first iteration. But anytime this gets updated, we're always going to be checking to see if max depth is greater than the current depth that we're passing in. And anytime that depth does exceed max depth, it will update this value accordingly. So then we can go through, we can check to see if there are no children. And I can see that like I wrote my solution up above a little differently than what we came up with just now. So we're going to check to see if this works. So we can say something like if tree.left equals should be null, and tree.right equals null, then we're going to return. And then otherwise we're saying there's probably a left or a right somewhere. So we can check to see if that's working. So we can say if tree.left, then we're going to recurse on tree.left, and we're going to just increment our depth. And I misspelled recurse. And then we're going to do the same thing down below with tree.right. Okay. And we're just going to see if this works. So we're going to run the code, see where we're at. Wrong answer. Okay. So let's see. Our root was 1, our output was 1, and they were expecting 2. So why are we getting the wrong answer here? We are expecting that if we pass in 1, we're going to call 1 with a depth of 1. We're going to then check the max depth, which should update max depth to 1. And we're checking to see if tree.left equals null and tree.right equals null. And if it does, then we're going to return. And in this case, it looks like tree.left is going to be null, and tree.right should be 2. So this should return correctly. Tree.left equals null, and tree.right equals null. So I'm not really sure if this is ideal or not. So what I'm going to do is I'm going to test this out. I'm going to see if my assumption is incorrect. So now I do want to return if this happens, but before I return, I'm going to console log tree.left and the right tree.right as well. And we can check to see what we're getting here, if this is indeed where the error is. Okay. Oh, and maybe one other thing to check here would be what our current depth is. Okay, so at depth of 1, which is the first one that we passed in, we are already returning, and that's not what we want. So this probably isn't the right logic here. So what's happening here is we're saying if tree.left equals null and tree.right equals null. So the whole thing should evaluate to a Boolean. And if it evaluates to true, then we're going to step inside of this conditional. If it doesn't, then we're going to step outside of it. So I kind of want to go back to my original solution here, and I am running out of time here. So I'm going to leap ahead a little bit here. And this was, these were a couple of the things that I ended up working through. So giving you kind of a flash forward here. This is something that y'all might encounter, or you might have already encountered. This is called optional chaining. And so this is a shorthand way of being able to check to see if a property exists. So this is going to check to see if tree exists before trying to execute .left. The original edge case that we talked about was the root being null. So I believe I wrote that over here. If there's an empty node as root, then we need to return 0. So here we have root equals null, return 0. And then we're going to recurse. We're going to do the same kind of general logic, but we're not going to worry about doing this initial check. We're just going to check down here to see if we are good to go. And if we check outside of here, just for the initial root, then hopefully this works. No, it's not working. Okay. Let's see, where are we missing something here? So we have let max depth equals 0. If root is null, return 0. We're calling our function. Tree and depth, max depth is being updated. We're checking to see if, I'm wondering if there's something to do with this incrementing that's occurring, if this isn't being updated appropriately. And then we're cursing on root and 1. So we're going to try this. And that was it. So depth plus plus in my mind should have worked. This is something that I'm going to like take a note of, because even though the problem got solved, I don't know exactly why depth plus plus didn't auto increment from the initial depth. So for me, what I would do is from here, just search plus plus operator in JavaScript. And this is my to-do list. So this is what I would start to study and get an idea of like, well, why wasn't that working the way that I was expecting it to? Was it specific to the environment that we're in? Is it something to do with my understanding of how the incrementer operator works? And yeah, so this was kind of a general introduction to my problem solving process within whiteboarding, and then as well as just like the sample problem. But that concludes today's lecture. If y'all have any questions, happy to answer them now. And I will stop sharing the screen now. Tom, Excalibur gives you, I believe you can make as many as you want. I haven't gone past the initial board yet. I just keep condensing all of my drawings into little buckets that I can reference later. But I think you can have multiple pages.
Can I ask about your question mark thing?
Yeah.
When you did if tree question mark dot left,
Mm-hmm.
how is that different than just if tree dot left? Is it acting different if it's null or something?
Yeah, exactly. So with optional chaining, that's what this is. So if y'all want to read more about that, it's optional chaining. It's an ES6 syntax that you can utilize, and it will not run the code on the right-hand side of the question mark if the declaration beforehand, or if the definition beforehand doesn't exist. So in this context, if tree was null, then it wouldn't even check to see if there was a left. It wouldn't bother with it. It would skip right past it. And it would just say, go to the next line. This is especially useful in asynchronous functions, when maybe you know that something's gonna get updated at some point, you know that eventually you'll have a reference to it, but you don't have a reference to it immediately, you can use optional chaining to prevent errors from popping up that would otherwise crash your app. You can just say, if this thing doesn't exist, just don't render anything. But if it does exist, then render it. And it's a shorthand way to be able to write that. You could also write if tree equals null, or if tree does not equal null, then if tree.left, recurse on tree.left and depth +1. That'll be another way to write it. It's just a little longer and more verbose way to write it.
Okay, I like it.
And yeah, Brett with and William with ES6, I think y'all started to do some implementation of this with pseudo-classical. And then I believe it's either next week or the week after where the constraints are lifted off y'all and you can just start to write in ES6 all the time. And it is very nice. It becomes a lot easier to read code quickly, I think, and to write code fast. Super, super nice. And yeah, like taking out curly braces, it doesn't seem like that big of a deal, but later on it does become quite simple to read through all these things. Yeah, Tom.
So I want to ask about like you're searching through a tree, obviously, and there's something missing in me bridging the gap between like Josh is searching through a tree and just looking at your input, because I'm not interconnected enough yet to look at an array and say, oh yeah, that's a tree. So can you walk me through that a little bit? I mean, like,
Yeah.
To my untrained eye, it looks like an array with values, and I understood you explaining how they correspond to this tree.
Right.
Is there something in JavaScript? Is there something implied or under the hood that simply says, oh, I see this array and I'm going to treat it like a tree?
Not necessarily. So this output here, if we set something like console.log root, we'll get an idea of what this is, and this is probably going to return another array here. But root is the representation of the entire. Let me think about how to say this. Root has a .val, root has a .left, and root has a .right. So therefore, roots.left is a part of root. Roots.left is also a part of root. So no matter how far down the tree you go, the furthest child down is still a part of root, so you can represent it as this array. And there are different ways to order the array. So when I see an array for a tree structure, one of my first questions is how was that array created? So there are different ways that you can create this array. You can say, let's go depth first search, and let's go 3 to 9. Okay, there's no more children, and then go to 20, and then go to 15, and then go to 7. And we could decide to not include nulls, or we could be explicit. We could say we go 3 to 9, and we're looking to see if there's any children. Nope, that's null. Okay, nope, that's null. And then we are inserting them as we go along. You can do breadth first search as well, which actually this looking at it is breadth first search. So we're going 3, 9, 20, null, null, 15, 7. And that's why the output is this way. But we don't know that by just seeing the array, because the order could be 3, 9, null, null, 20, 15, 7. Could also be 3, 9, null, 3, null, 9. I'll take that back. What is pre-order, post-order? I think it starts at null, null, 9, 3, and then 15, 7, 20. So there's lots of ways that you can order this, and it's basically how the searching algorithm is structured. So we don't know right away. So I would start off by console logging root, and then I would also console log root.left and root dot right and see what that looks like. And so here I'm going to see something hopefully more explicit, so I can see standard out. Okay, so we know that this is our root, and we know this is my root's left, and we know this is my root's right. And again, these are all of the rights, all of the right values, as far nested down as they're going to go. These are all the values as far nested down on the left as they're going to go. So from there, I can start to infer, oh, okay, so there's a couple nulls here. 20 does have some values here. So I can probably assume that nulls are belonging to that, but I can also say root.left.left and root.right.right and confirm my suspicions. Ooh, cannot read properties of null reading left. Okay, well, that gave me my answer, right? Even though it's an error, now I know, oh, okay, well, I can't access that, I'm guessing. In a linked list, maybe you could. In a tree, in this context, apparently you can't. But it also gave us our answer. So if I take this out and I say, well, I also wanted to make sure that root.left.right is null, I'm expecting I'm going to get the same error. And I do.
So
I get the same error.
is it essentially that I was having trouble looking at the array because I wasn't entirely aware of this, I think I'm using the term correctly, inherited property of left and right?
You're looking at the array, and I think you see it as a list, as just like a straight list. But we don't know enough information just seeing a list. Like we can't tell what the tree structure is just by getting that. So this actually isn't enough. This is why they have to include the visual as well. They could also say, instead of this, they could say this list is represented as a pre-order list or a post-order list. And so this is some further reading for when you eventually have some time. Post-order versus in order versus pre-order. And here we go. So this would give you some insight into how some of these are constructed, or how some of these searching algorithms are constructed. But yeah, like you wouldn't, I don't think these are things, I think this is important to maybe recognize as like kind of general concept. You might not be able to intuit through everything. A lot of this stuff, like what I was just working through there, was based off of reading a lot of docs and going through all the lectures in junior phase, going through lectures in senior phase, working on problems. So if you can't intuit something, it's not a fault of your own. It's usually just, you probably haven't been exposed to that concept, or you haven't been exposed to it enough at least. And so you just need to re-expose yourself to it. So in this case, if you had no idea what this was, I would at that point try to just go through this and see if I could intuit some understanding of it. And if I couldn't understand what was going on from these console logs, that's when I would reach out to somebody. I would usually like reach out to, yeah, go ahead.
So it's the presence of the diagram that says, oh yeah, this array represents a tree.
And
That's where I was like, okay, I see this tree diagram and I know what I'm looking at there, and now I see this array, and
yeah,
you need one to confirm the other, kind of.
Exactly.
Okay.
Yeah,
I thought I was supposed to confirm that the array was a tree just because I'm so awesome or something.
Yeah, no, it doesn't always work that way. You'll see these things kind of written as like shorthands often. Trees, graphs, linked lists, things like that. They'll often look kind of like this. But you can't always assume that you know what exactly it's supposed to be representing. You have to do
okay. Thank you.
I think I saw somebody else's hand up. Yeah, Josh.
Yeah, this might be very irrelevant to this lecture, but you know how you're reaching the max, getting the max step by that function? And you would want to do that every time you insert a node, right? So just for the time complexity, wouldn't I was thinking about like approaching the way how having max step every time, updated every time from the root node or root of the tree. Would that be not efficient for space complexity wise?
Can you describe that again to me?
So having max depth updated every time I insert something, or not every time, but when I'm inserting, I have like this depth value keep updating. And when I finally insert that node, I would have update that max depth value of my root node. So that will take up space and more steps involved inside inserting method. Would that be not efficient? Or
I don't think I'm fully following. So in this case, can you tell me like where the first line change would be from what you're?
oh no, like not using that method at all, like searching for max depth, but by function, how you traverse the whole tree.
Mhm.
But I was saying inside the insert function, I would keep track of depth
I see.
every time I recurse.
When you're building out the entire class, like so instead, like
Yeah,
so we
yeah,
have
yeah.
something like we would have an insert. We have like tree node dot prototype dot insert, and we would pass in like a value and a depth.
Uh-huh.
Is that what you're referring to? Or maybe not
Yeah.
passing in the depth, but adding the depth to the value as we're going through. So do some work through insertion and discover depth along the way. And maybe here we would have a this dot depth equals you could do it like that. That would work. And so you're right, right? This would increase the space complexity of the tree itself. Thinking through it, in a tree, right? If we're given the root node, would that increase or would that make our time complexity more efficient? I think we still have to traverse through the entire tree structure anyways. Unless you're proposing in the initial root in this first value, we differentiate that from all other tree nodes, and we're always trying to update the root. In that case, we would also need to have some function that would, or some method that would allow us to look for the root each time as well. Anytime we're doing any kind of insert, which I guess we would just start at root anyways. We would have something like maybe this dot root.
Yeah, I mean, since I was thinking of a binary tree, you always start from the root, right?
You do. Yeah, so you could possibly add some more parameters inside of root itself then. And yeah, you would trade off some space complexity for increased efficiency. So you would end up with an O of 1 time complexity for looking up depth at any max depth. So I think usually what like you'll see in these kinds of cases is like trees can take a whole bunch of different shapes. So you can run into cases where each value or each tree node itself does contain a reference to its depth. It's not necessary, it's not guaranteed. It's like it depends on the use case, I think. In the case of an HTML DOM, I don't know that it would like ever really matter like what the max depth would be, right? But probably we need to maintain some reference to the parents and to the children. And in this case, it's not a binary tree, right? It's just a tree because we can have any number of children for any parent. But in this specific use case, if you were to say like, I want to maximize the time efficiency for max depth, then sure, like, yeah, I think that makes sense. Like you could add in some extra parameters to the root value and then update that every time that you insert a new node. I think that's a really good idea.
Thank you.
Pre-order is clockwise, post-order is counterclockwise. Cool. I like the way to think about that. I always think about pre-order, post-order, and in order from the order of the recursive calls. So like usually like recurse left, recurse right, and then where are you pushing your value? So if you like have like, you know, your so something like this, order dot push, whatever the, you know, tree dot val is. This is pre-order because we're pushing before we recurse. In order, we push in between recursing left and right. And then post order, we push after we have recursed left and right. And so those output different different final orderings. So like based on Tom's question earlier, this order here would change depending on when we decide to push relative to when we're recursing left and right. And I believe recursing left and right is just by convention. I don't think there's like any like special reason for that. Like I think we probably could also do right and left, but I don't think you really see too many algorithms with right and left. Sweet. All right, y'all. Well, if anybody has any other questions, let me know. Thanks for coming out. Super fun. And I believe y'all have some time here, so feel free to take a few minutes, about 10 minutes before our next scheduled block. And yeah, then we'll get into the next set of things.
You're still recording, by the way, but I have a separate question.
Okay. Is it recorded? Is it a question for the lecture?
No, I'll hold off then.
Okay, let me stop recording then.